All right, let's jump right into one of the most, and I mean most, fundamental ideas in all of machine learning: distance metrics. So, what are they? Well, you can think of them as the rulers, the measuring tapes for our algorithms. They're the tools that let a machine figure out what's similar, what's different, and really make sense of all the data we throw at it.
So, how does a machine even measure something like closeness? I mean, for us, it's pretty intuitive, right? We just see it. But a machine, it doesn't have eyes or intuition, it just has numbers. So it needs a rock solid mathematical formula to calculate exactly how far apart two things are. And that's precisely what a distance metric is.
And this isn't just some abstract academic thing. No way. Distance metrics are the absolute foundation, the bedrock, for some of the most popular and powerful algorithms we use every day. We're talking about things like k-nearest neighbors for classification, k-means for clustering. These guys wouldn't work without them.
At the end of the day, these metrics are what give an algorithm its power to group similar stuff together and separate things that are different. But here's the kicker. The specific metric you choose completely changes how the algorithm sees the data. It's like giving it a different pair of glasses. What it sees, the patterns it finds, and the quality of its final results, it all comes down to that initial choice.
Okay, so let's start with the two big ones, the workhorses of our toolkit, the absolute essentials. Think of these as the hammer and the screwdriver of distance metrics: Euclidean and Manhattan distance.
First up, we've got Euclidean distance. And I bet you already know this one, even if you don't recognize the name. This is the one we all learned in geometry class. It's the most intuitive way to measure distance, right? Just the shortest, straight-line path between 2 points. We call it the as-the-crow-flies distance, and it's perfect for when your data points group together in nice, compact, kind of roundish clusters.
And then we have Manhattan distance. And yeah, it's named exactly for what you think: navigating a city grid like Manhattan. You can't just fly through buildings in a straight line, can you? Nope. You have to follow the streets. Go a few blocks this way, a few blocks that way. This metric does the same thing, summing up the distances along each axis one by one.
So here's the key trade-off between the two. Euclidean gives you that nice, intuitive shortest path, but it's really sensitive to outliers. Those one or two weird data points can totally throw it off. Manhattan, on the other hand, is way more robust against those extremes. And, big bonus, it's often computationally faster because it avoids all those messy squares and square roots. That's a huge deal when you're working with tons of data dimensions.
Okay, but what if I told you that Euclidean and Manhattan aren't actually two different tools? What if they're just two different settings on a much more powerful, kind of universal metric? Well, let's meet the Minkowski distance.
Minkowski distance is kind of like the Swiss Army knife of metrics. It's this one generalized formula that has a special little knob you can turn, a parameter we call p. And just by changing the value of p, you can completely change how distance gets calculated. It gives us this incredible flexibility. And here it is. This is the big aha moment. When you set that little parameter p to 1, bam! The Minkowski formula turns into the exact formula for Manhattan distance. And when you set p to 2, you guessed it, it becomes the formula for Euclidean distance. They're not separate things at all. They're just two special cases of this one powerful unified idea.
And believe it or not, it gets even weirder. Here's a really mind-bending fact for you. We're taught that a straight line is the shortest path, right? Well, that's true in our 2D and 3D world. But in the weird high-dimensional spaces where our algorithms live, setting that p-value to something greater than 2 can actually define a path that's even shorter than the straight line Euclidean distance. It's a crazy but fascinating glimpse into how different geometry is in these abstract worlds.
Okay, so everything we've talked about so far has been about geometric distance, points in a space. But what happens when you need to measure something more abstract? Like, how similar are the topics in two different articles? Or how much do two people's tastes in movies overlap? For that, we need to pull out some more specialized instruments. First step is cosine similarity. Now for this one, I want you to forget about distance for a second and think about direction. Cosine similarity is all about the angle between two vectors. It literally doesn't care how long the vectors are. That's their magnitude. It only cares about the direction they're pointing. If the angle between them is small, they're super similar. If the angle's big, they're not. And this is a total game changer for text analysis. Just think about it. You've got two articles. One says machine learning is complex, and the other says machine learning is difficult. Now we know they're talking about the same thing, right? Cosine similarity gets that because the vectors representing those sentences will point in almost the exact same direction, even though the specific words are different.
All right, next up is Jacquard distance. This one is super intuitive. It's all about measuring the overlap between two groups of things, or sets. The way it works is simple. You just look at how many items the two groups have in common, and you divide that by the total number of unique items across both groups combined.
This is absolutely perfect for recommendation systems. Let's say we want to see how similar your movie taste is to your friends. We'd use Jacquard. We just take the number of movies you've both liked and divide it by the total number of unique movies that either one of you has liked. It's that simple, and it's an incredibly powerful way to find people with similar tastes.
And our last specialized tool is Hamming distance. This one is so simple. It's for comparing two strings that have the exact same length, and all it does is count the number of spots where the characters are different. That's literally it. Simple as that. But that simplicity is its secret weapon. For example, if you compare the strings Gattaca and Gattatada, you just go letter by letter, and you find only one difference at the 6th position. So the Hamming distance is 1. This simple idea makes it incredibly useful for everything from spotting errors in computer code to analyzing similarities in DNA.
Okay, so we've laid out the entire toolkit. We've got our rulers, our compasses, our specialized gauges. But, being a master craftsman isn't just about having the tools. It's about knowing exactly which one to pull out for the job. So let's talk about how you choose your metric wisely.
Think of this as your quick reference guide, your cheat sheet. If you're dealing with something geometric, like actual map data, or you have nice dense clusters, Euclidean is a great place to start. If you've got tons of dimensions or data that feels like it's on a grid, Manhattan is probably your best bet. It's just more robust. Analyzing text, you're going to want cosine. Comparing what different users like, Jacquard is your friend. And finally, if you're comparing strings or checking for errors, Hamming is the no-brainer.
And I really have to stress this choice is not a minor detail. It's a critical decision with huge real-world consequences. If your distance metric doesn't actually capture what similarity means for your problem, your algorithm is going to group things in a way that just doesn't make sense. And that can lead to more than just bad accuracy. It can lead to unfair, biased, or even harmful outcomes.
So I'm going to leave you with this one thought. Your choice of distance metric, that's the ruler you hand to your algorithm. And just like using a yardstick versus a microscope, the ruler you choose completely changes what your algorithm is able to see. So the big question you have to ask yourself isn't just which tool should I use, it's what do I really want to measure? Your choice defines the world your model sees, so choose that ruler wisely.